Peter Palffy-Muhoray.
Thank you. Okay, so I'm grateful to the organizers for the opportunity to speak. I want to say a few words about modeling multi-component systems. This is work with my colleague Xiaoyu Zhang from the math department at Kent State, and we are happy to acknowledge support from the National Science Foundation. So this is really very much work in progress, and probably this talk is a little premature, but we were so filled with youthful enthusiasm that I thought I would tell you about it. So a quick outline, I want to say a few words about motivation, talk about single component systems, multi-component systems, a few words about phase separation in binary hard particle systems, some thoughts about modifying Onsager theory, and a quick summary. So why are we interested in this? So most commercial devices use liquid crystal mixtures, and often they're not really interesting. They basically have a linear sort of extrapolation between the properties of the individual systems. But more interesting are systems where people put additives, impurities, nanoparticles, and so on, where even small amounts can fundamentally change the behavior of liquid crystals. And so, for example, an interesting fact is that you can only put a very small amount of nanoparticles into liquid crystals. So why is that? You know, where does that limit come from? Okay, and lyotropic liquid crystals are inherently multi-component systems, and colloidal systems, as we have heard, can be liquid crystalline. So lots of reasons to study multi-component liquid crystals. What is the problem? Well, the problem is that most theories are for single component systems. Meyer-Soper theory, Landau theory are basically written for a single species. So how to model multi-component systems? Well, one can use sort of standard conserved order parameter dynamics to talk about multi-component systems. And so the question is, what do we need? And what we need is free energy of multi-component systems in density functional form, ideally including both soft and hard interactions. So that's really the goal, to try to get this. Now, we've heard beautiful talks on density functional theory by Lev Langer earlier on and by Bob Evans. But what I'll do here today is really something much simpler and more pedestrian. So now, just a few words about modeling. So if we have multi-component systems, particles are conserved. So a useful quantity is the number density of particles at a given position in space with given orientation at some time. And one can define this for the different species, and then one can get essentially all relevant information, moments of the distribution, and so on from these. And the dynamics is essentially just the equation of continuity for particles. So the density changes due to the divergence of the currents, and then we have currents both in position space and orientation space, and maybe we can have other internal degrees of freedom, but certainly the general strategy would be this. Okay, and then the question is, what drives the currents? And what drives the currents are forces, which, so this is the currents and the velocity in overdynamic system is proportional to the force. And the force can come from any sources, but certainly one source is the gradient of the chemical potential. Of course, there are dissipative terms as well. We can hopefully generate those. But to get the chemical potential, we need to have the free energy density, which then gives us the chemical potential. So again, the key is to get the free energy as function of these densities.
Peter?
Yes?
I understand, before you go on, how does the current, the orientation current, affect the density?
So the density is the number of particles per volume of generalized coordinates. So as a function of both position and orientation. So a simultaneous. Okay, So here's a few words about things that everybody knows. I want to think about the canonical ensemble. So we imagine, as Gibbs proposed, that we make a supersystem composed of many, many copies of our system under consideration. Each system has n particles, temperature T, and we make an ensemble of these, and then we ask how energy distributes itself over these over this ensemble. And I'm sure everyone knows that, subject to the constraints that we have, that the most probable energy distribution is just given by the ratio of the Boltzmann factor divided by this weighted sum over all states. So this is really straightforward procedure everyone knows how to do. And so one can define the partition function as the term in the denominator, which and then one defines the free energy as minus kT times the log of the partition function, and then these two are related, so we can write the partition function in terms of the free energy as well. So now, why I bring this up is simply that we don't have to have an infinite number of particles. We don't have to go to a thermodynamic limit in the number of particles in our system. The other point is that the free energy, which we can calculate, is just a number. If you simply perform this sum somehow, then we just get a number. There's no quantity here with respect to which we can minimize the free energy. So it's interesting to then ask the following question: what is the probability that our system satisfies some given constraint? So we can ask, what is the probability that, let us say that the average value of P2 in our system has some numerical value, say S. And so this is the probability that our system is in state I. And then the probability that we satisfy some given constraint then is obtained just by simply summing over those states which satisfy the particular constraint. So this is a trial free energy, and it's just a subset of all the states that we could sum over. And given that we can write the partition function in terms of the free energy, we can write this restricted sum over states as in terms of the trial free energy. So this is the trial free energy. This is what we normally work with. And so this is the free energy, which is obtained by summing over those states which are compatible with the constraint that we have. And I point this out because so this is a nice way, I think, of thinking of imposing constraints on the system. Okay, so the two observations then is that the number of particles doesn't need to tend to go to infinity, and we want to evaluate the trial free energy, that is a free energy subject to some constraint that we impose, and then later we can try to make this free energy a minimum, which gives us the highest probability, which is what we will observe. Okay, so let me quickly look at a single component system. So Helmholtz free energy is just this. Now how to evaluate the partition function. So Sommerfeld quantization tells us that in each, okay, so we write the energy in terms of the Hamiltonian, so in terms of generalized coordinates and the conjugate momenta. Sommerfeld quantization tells us that this is the density of states, so we can sum over the states and evaluate the partition function, at least in principle. Now, in almost all cases, we can integrate over momenta, and that just gives an additive temperature-dependent constant to the free energy, which is usually not important. So we really want to focus on the configurational partition function, which then only contains generalized coordinates and the energy. And then it's customary to assume that interactions are pairwise, okay, and then we can write it like this. And because we have indistinguishable particles, we have to correct for overcounting. So this is the configurational free energy. And next, it's nice to focus on one particle in the system, say particle labeled 1, and then one can look at its interaction with all the other particles in the system. And then, of course, we have all the other particles to worry about out here. Now, a useful thing is to decompose the potential into a slowly varying long-range attractive part and a rapidly varying short-range repulsive part. And then the sum of these are the potential that we'll be working with. And then the free energy, okay, just separating the interactions into repulsive and attractive parts looks like this. And then one can rearrange things somewhat. So here are the repulsive parts and the attractive parts. And so without justification, we can simply rewrite each of these terms by adding and subtracting a 1. And then we have this product, and we can expand this product and just keep the leading terms. Okay, and we leave the attractive part of the energy out here. Now we could look at higher order terms, but for now we'll just stop at this term. So this is the ends up being the second term in the virial expansion. And then we turn to the usual mean field approach to replace things by their average value. So for the attractive part of the energy, we have all these terms up here, and we argue that we can approximate these by simply integrating over the density, the attractive part. And then assume that somehow this averaging maintains the essential features, and we can replace this term in the integral by this single particle potential, which now only depends on the generalized coordinates of the particle under consideration. So we have an effective potential and a procedure for prescribing it. Okay, and then we can try to do the same thing for the repulsive part. So now the reason we can't do the same thing for the repulsive part is because the energy is infinite if you interpenetrate, or 0. So when you average it, it's infinite. So that's why one has to sort of work it down to ground level. But this quantity is well behaved. If particles interpenetrate, this expression is 1. If they don't see each other, then this expression is 0. So one can again average this quantity in the same sort of way, just integrate over the density. And this, of course, can be written in terms of the Meyer function that we've heard about. And this is a kind of a single particle excluded volume fraction. It's a dimensionless quantity, and this sort of corresponds to the excluded volume. And then again, we assume that this product of the hard particle terms can be written in terms of this excluded volume fraction. So here it is. This is sort of the definition of the excluded volume fraction term. Now, so then we do the last step, and so we've taken care of what particle 1 sees, and then we argue that all particles are equivalent, so everybody has to see the same world. And so then we have the free energy containing the attractive and the repulsive part. And again, this generalized coordinate typically would be position space and orientation space and whatever else we may have. So this is really simple, and I'm sure most of you are familiar with this. And I just want to give a simple example. So if we have spherical particles, then the single particle energy is proportional to the number density of neighbors times some average London dispersion energy. And this excluded volume term looks like the number density times something like the molecular volume. And then we have the free energy. And then if we take its derivative with respect to volume, we get the celebrated van der Waals equation of state, which we know describes everything in a really nice way. Now, I think it's really important to be able to get a density of states. as Amparo Galindo mentioned yesterday. So I think that we ideally should shoot for something that's capable of at least giving us this. And so one key aspect here is that there's a critical density where the pressure goes to infinity. You start to compress the system, at some point you hit the wall, right? Temperature is fixed. When this thing approaches 0, P has to go to infinity. I think Van der Waals got the Nobel Prize for this equation, what, 100 years ago, more or less, I think. Okay, moving on. So this logarithm term, I think, is really important. This gives us liquid-vapor coexistence. If we do some expansion of this term, just have an imperfect gas. Okay, so now let me turn to the problem of prescribing a given density to a system. So we try to get the free energy given that rho is prescribed. And here, one way to go is to take now not a super system, but a real system, divide it into sub-volumes, and assume that the number density is slowly varying, so it's essentially constant in each sub-volume, and we'll assume it's isothermal, though it's not necessary. So in the ith sub-volume, then, we have Ni particles, and the volume of that little piece will be delta V, delta omega, and whatever other variable we may have. And since the free energy is additive, or even if you think back to the way one calculated it, integrating over phase space, we simply have to add up the free energies of all these little pieces, and we can just use the expression that we had before for the free energy density of a uniform system. So we have to, because we are summing, we have to take the product here, and in each little sub-volume we have Ni particles. So this is then the free energy of our entire system when we do the sum. And because our energy and density are slowly varying, we can dispense with the integral. We do Stirling, and so the element of volume and n coming in from Stirling give us the number density here. And up in the exponent, we can write the number of particles, again, in terms of the density and the element of volume. So we have a kind of a continuous product here, which, when we take it outside of the logarithm, gives us the integral, right? So one, in this way, ends up with kind of the standard forms we've seen. We see the integral of rho log rho, first of all. I put in a Lagrange multiplier to conserve particles. And then we have the hard particle terms coming out. So we have rho log 1 minus this excluded volume term. And I wrote explicitly now the coordinates over volume and orientation. And we have the attractive part, again, the same kind of structure. Density, density, interaction kernel, and coordinates. Now, if we just forget about the attractive part, and if we expand this logarithm, then we have the Onsager free energy, right? But this is what we end up with normally. So this is kind of the story. Now to do a multi-component system, it's just the same. It looks a little horrible, but it's really very simple. We just keep track of the different species, and we get the same free energy. So for species A, we have rho log rho, again, number conservation. We have the excluded volume term. And now this is interesting because we have two kinds of excluded volumes, self-excluded volume AA and AB, which we have to take into account. And the same is true for the attractive part. We have AA and AB attraction. And then for species B, it's exactly the same story. So all we need are the interaction kernels between AA, AB, and so on. And in principle, we have a fairly compact expression for the Helmholtz free energy. And incidentally, this gives the elastic constants because we have the kernels. So if you expand rho in some gradient expansion and do the integral, then we get the elastic constants in the more or less the usual way. And in principle, this should also give us equations of state. and all the various things you're looking for, phase diagrams, chemical potential gradients, and so on. So there's a really simple way of getting an expression for the free energy. Okay. Now I want to think a little about phase separation in binary hard particle systems. So this is a really fascinating concept. Why would things want to phase separate in the first place? But one can imagine that if you have a mixture of two kinds of things, and if the excluded volume for the different types of particles is really large, then it's better for particles to phase separate, have small excluded volume, and more configuration space to span. So if the excluded volume between different things is bigger than for the same thing, then one would expect that. Of course, we know that in reality we have this beautiful depletion interaction story proposed by Asako Enosawa and Jean-Pierre Hansen and Dan Frankel have done beautiful work on this. But at this level, we don't have in our theory depletion effects because those involve three particle correlations. Of course, we could have gone on with our expansion, but as we stand, we don't have depletion interactions. We can still ask, will large and small particles phase separate? And so it's useful to define the average excluded volume by essentially averaging this excluded volume term over both particles orientations. Yeah, this should be an A, I apologize. It should be rho A, rho B. Anyway, so this is the average excluded volume. And either for an isotropic system or a perfectly oriented system, so we could imagine that we have external fields keeping one particle aligned one way, another the other way. The free energy becomes simply rho log rho and this excluded volume term for one species and the same for the other. And then we can ask, will this system be stable against phase separation? So we need to look at the Hessian, the derivatives of f with respect to the rhos. And it's maybe worth mentioning just one thing quickly, that if we have a given composition, and so say rho A and rho B are given, then the system will have a corresponding free energy. Now, if the system were to phase separate, it would have to separate into two components with different composition. So suppose one of those compositions is there, then particle conservation requires that the other composition be on a straight line joining this point and the original composition. So it'll have to be on that line. And the distance depends on how much of this phase you have. So this is kind of the situation. And then each of those different composition phases have different free energies, but the free energy of the system happens to lie on the line joining those energies exactly above the original point. So the question then is, can the system lower its free energy by separating into two different compositions? And so the convexity of the free energy surface answers that. So, yeah, so we need to look at the curvature. And now, if we expand the logarithm in the free energy, then we get this really nice expression for the free energy, just in terms of the densities and the excluded volume. And the determinant of the Hessian is this thing. And there is this interesting term here, which is the sort of excluded volume between the different species squared divided by the individual ones. And if this gets big enough, the system will phase separate. And for hard spheres, it's sort of trivial to calculate this. And so it just ends up being the ratio of the radii and the inverse of that. And we can make that arbitrarily large. So this system is unstable against phase separation if the spheres are different enough in size. So it's unstable, and if you look at rods and plates, you get the same result. So we get phase separation just due to differences in size in this model. Now, if you don't expand the logarithm,
Here, I'm sorry, maybe I'm being dumb in that. Even if they're the same size, 4 cubed is bigger than 1, right?
Factor of 8 somewhere.
There's 8 missing,
Or 16.
apparently, or 64.
no, I checked it. For the same size, they don't phase separate for sure.
But that's
So-
4, right?
So yeah, so I must be missing a term here. But yeah, no, I checked it carefully. Yeah, sorry for the typo. Okay, now if we don't expand the logarithm, it turns out that one can bite the bullet and do the Hessian, and it turns out to be positive definite. So, system is always stable. So the point here is that one gets really fundamentally different model predictions depending on whether or not we expand the logarithm. So I think that that's important. All right. I want to say a few words now about Onsager theory. So again, take the free energy of this of a one-component system. It looks like this. And if the number density, that is without regard to orientation, is constant, then it's convenient to write it just as a number density and an orientational distribution function. And the free energy then looks like this. And here's the excluded volume term. Now, this excluded volume is obviously all important. Onsager considered long cylinders, and in the limit when the aspect ratio gets very large, then the excluded volume has this form. It looks like the sine of the angle between the axes of the two cylinders. Okay, now, this is a beautiful result, but it turns out to be pretty intractable, although it looks simple. And so instead, we thought about ellipsoids, and as we've heard again already, that there have been approximations for ellipsoids by Struve and Leckerkircher, and it's essentially the same as this. The excluded volume basically is proportional to P2, and so this is a sort of a kind of a scaled volume, and nu and eta are just aspect ratio dependent terms. And eta is particularly important. It is basically the asymmetry of the particle. So if it's a sphere, it's 0. If it's something else, it's something else. Now, if you look at the excluded volume, so the essential features are the same for both of these situations. When the particles are perpendicular, the excluded volume is big. So the difference really is down here, and you can sort of see why that is, because you have the straight sides. When you make even a little angle, the excluded volume increases. Now, whether molecules really behave like that is a moot point, I think. But I would argue that given that these are both approximations to what molecules do, the difference between them may not be all that significant. So now, if we expand the logarithm, then we get the usual Onsager expression. And then we need to minimize the free energy with respect to the distribution function. And I've written the orientational distribution function as this little f, whose argument is cos theta. And if you do the variation, then you get this simple looking expression for f, except up in the exponent, there's this integral over the excluded volume, which we cannot do. It contains the distribution function itself again. So it's a kind of a self-consistent equation, but it's really hard to solve because of the form of the excluded volume. So Onsager then postulated a kind of an ansatz for the distribution function. So this is not really tractable, but it gives an automatic phase at sufficiently high densities. The other expression, though, for the excluded volume is really tractable because we can average over the excluded volume, and we get exactly the Meyer-Saupe distribution function structure. So we get scalar order parameter S times P2, and instead of the temperature dependent term here, we get essentially the volume fraction times this anisotropy parameter. So it's exactly Meyer-Salpa alike. In fact, if you compare the free energies, this is the conventional Meyer-Salpa theory free energy, and this is the free energy get from the Onsager approach if we use this ellipsoid approximation for the excluded volume. So the structure is really the same, and there's this correspondence between the attractive potential and KT and the packing fraction and the anisotropy. And we know what Meyer-Salpa does. We know everything about the solution and the stability and so on. And in this model, we got exactly the same behavior, except instead of dealing with temperature, we have to deal with the inverse of the number density. So one gets a discontinuous transition to a nematic phase as the density is increased. And one point I want to make is that in Meyer-Salpa theory, we know if we do asymptotics that the order parameter is 1, that is the perfect order, when the temperature is 0. That means that in this hard particle picture, we get S equal to 1 when the number density is infinite. But that doesn't seem realistic because we have hard particles. There has to be a limit on the density that we can achieve. So that takes me to the last part of my talk. So if we use this approximation for the excluded volume and don't expand the logarithm, this is what the free energy looks like. And then now we have to look for f of x, which minimizes the free energy. And so this is maybe a little more interesting now. It turns out that there are two solutions. So this is, you can imagine the density or the volume fraction increasing downward. And one solution that minimizes the free energy is just f equals 1, which means that the system is disordered. And the other is a situation where f is a smooth function increasing with x. So this gives rise to order. But as you increase the volume fraction, this value of f at x equals 0 gets lower. And above a critical density, the function becomes piecewise smooth, so we get a discontinuity in the slope. And as you increase the density, we eventually get a delta function at x equal to 1. And so explicitly, we have one minimizer, which is x equals 1. And the other is more complicated. There's still an exponential factor, just like before, but there's a prefactor term which contains the volume fraction. And it basically says that if the volume fraction is high enough, particles cannot deviate from the ideal orientation because this term will go to 0. So it essentially prevents particles from being disordered. And so, of course, one has to normalize, and one has to normalize essentially over the region where f of x is different from 0. So we have this interesting quantity A, which is basically the point where you have the discontinuity in the derivative. And if you minimize the free energy with respect to A, then you find that f of A is given by this. So we can calculate what A is, and it depends on the density and the order parameter and so on. So one needs to see which solution has the lowest free energy. And if you do all that, then you get this picture for the order parameter. So this is S versus volume fraction. And so these are different aspect ratios. And the behavior is what you would expect. There's an isotropic phase. And then there's a transition, a discontinuous transition to an ordered phase. And this happens at higher and higher density as the aspect ratio gets smaller. And there's also a negative S solution in each case. And so these are the isotropic solutions. Now the isotropic solution simply stops at some point, unlike in the Meyer-Sopper case. The free energy becomes complex, and so the solution is gone. Interestingly, the value at the transition is close to a half. It doesn't change very much with aspect ratio. And these regions here are not straight lines, as one might think, but they're in fact curves. And if we look at the structure, they look something like this. So this is the order parameter versus volume fraction for aspect ratio 5. And we've colored these curves differently. And so this graph here shows what happens in this region, purple, yellow, blue solution. And so this is the free energy minus the isotropic part of the free energy. And it's quite complicated. It dips down and it comes back up again. Isotropic free energy is down here. So that means that in this region here, the isotropic solution is a lower free energy. But at this point, the behavior changes dramatically. So this is where the solution becomes, the derivative becomes discontinuous. And the transition actually occurs here, where the solution is already discontinuous. And the similar behavior happens in the lower branch here. And these are the two branches at slightly higher number densities. So the green curve shows this is the free energy of this oblate solution minus the isotropic part. And this is negative. So this shows that the oblate has lower energy than the isotropic one. And this red curve is the prolate solution minus the oblate one, because the isotropic disappears. And this has lower free energy than that one. So this is the lowest free energy solution. And it saturates, it goes to 1 at a finite density. So, well, that's pretty much what I have to say. So we have proposed this rather elementary scheme for generating the free energy for multi-component systems in this density functional form. And it seems to be a simple way to combine the effects of steric and attractive interactions. And a point that seems important is that expanding the logarithm can really result in very different model predictions. So likely it's better not to expand, although it's less tractable. I think there's more physics and more realistic physics in here. And then we looked at this simple model for hard ellipsoids, where orientational order saturates at a finite rather than infinite density. Good, thank you.
I think you can derive the starting point for your theory in 2 lines. You can simply write down the excess free energy in the way that Martin Schoen was indicating in the last talk. So you say, I'm going to write the free energy as the free energy due to repulsive interactions, and then you formally integrate over a coupling constant, which turns on the attraction. And if you set the correlation function there to be essentially 1, a constant, you end up with precisely your mean field treatment of attraction. So all of that is very well known. My concern is what you do with a repulsive piece. I mean, by taking a van der Waals picture, it is known that that is a lousy approximation for hard spheres anyway. The logarithm is just awful. You can do simply much better.
I agree.
Do much better.
I know, there's Carnahan starting, there's all sorts of
densities
things.
you're talking about.
But it's better than not having it, which simply doesn't give us
trivially bad.
Are we taking I mean, this is, you're surrounding your particles by a cage, right? And in some sense, you're varying the size of the cage, and you're saying that my particle can't shift out of the cage.
No, not so. No, the particles are not contained in the cage.
No. I don't mean that formally you put in a cage.
And they interact with all the other particles.
Yeah, but if your particles can't change can't reorient by a certain amount, right? Your distribution function is 0 beyond a certain amount of tilting.
Right.
So that one way of looking at that is to say that my particle is inside a cage. And
Right.
it's coming
true.
out of the cage, right?
Right.
So there has to be a way of deriving it which involves the cage. Anyway, my question is, if you reach a certain density at which you are changing, now it can't, the distribution function is 0 at pi/2. Doesn't that mean that you are implying some kind of thermodynamic singularity at the point at which the distribution function is going to 0 for the first time? I mean,
Singularity in what sense?
Well, some higher derivatives in the free energy would be presumably diverging or something like that as you reach
Not
that
obvious
point.
to me. Maybe, but
I mean, in any case, isn't it possible you haven't included smecticity here? Isn't it likely to be cheaper to confine myself in the in the perpendicular direction rather than have a...
I didn't understand the last one.
Okay, instead of restricting the amount of what happens to a disoriented particle, right? Isn't it likely that you are restricting you change the one particle distribution function? So you introduce
Sure. But here, I assume that the number density was constant. I mean, you wouldn't do that in general. This is just under
And I
that
was thinking
assumption.
that maybe that your sort of peculiar behavior of the distribution function would be preempted by the formation of a symmetric phase.
Oh, that could well be. But here we assume that the number density was constant, just for simplicity.
So let's thank speaker again.